Murilo Junqueira, lead engineer at Hitachi Astemo Americas Inc., as he introduces groundbreaking advancements in damper model integration using artificial intelligence and deep learning methods. In an era where full vehicle simulations are increasingly crucial, the demand for sophisticated damper models is on the rise. This presentation explores how deep learning techniques can revolutionize damper modeling, simplifying complex simulations and enhancing accuracy.
So, good afternoon. My name is Murilo. I work together with Omar and Claudio on this project. So, I'm representing Hitachi Astemo. Hitachi Astemo is an integration from other suppliers like Heihin, Showa, Nissin, and Hitachi Automotive Systems. We provide powertrain systems, chassis systems, motorcycle systems, and autonomous driving and advanced driver assistance systems. So I'm very excited about this matter because I could see a lot of progress on the conversations that we had, mainly on the last podium that we had the discussions because the integration and suppliers and the OEMs. So as we all can see, the tier one suppliers, they are being pushed to follow the pace of OEMs on the virtual path. And we are Astemo, we are being proactive on this. And we are investing on tools and developing new methods to be side by side with the OEMs. And one of these methods is a machine learning solution that helps to improve the representative of damper models, and as well, it will help the immersion when applied on driver in loop simulations, for example. So the most common way that we are used to do the damper model on full vehicles, it's using that we call as a lookup table that we just take a small picture of all the damper behavior and put on a table with values of force at peak velocities, but we are losing some of the damper behavior on this path. We can have like several different valve codes of dampers that they will give the same valve, the same peak force velocity curves, but they have totally different behavior. So like we can see on these blue and red football curves, these lag that we have on the blue lines, they will affect and they will have a totally different response on the vehicle, even on steering, on ride as well. But when we go in to put on the model, if we are going to use the lookup table, they will be the same values. So we are not going to capture these on a full vehicle simulation. Another way that we can see is that on that point of that we can see how a lot of the hysteresis on the damper, and those lags, they can be shown on the right side of the plot. So all those 4 plots, they have different behaviors of damper, but they all have the same peak force on the given velocity. So different behavior, but using lookup tables, it will be mostly the same. So there's some alternative ways that we can improve our damper modeling. One of those is doing using that we call a 1D dampers that we can include fluid properties, and we can include the representativeness of each of the components, but these will require some knowledge from the system. So we can do this for our dampers, for example, but if I'm going to do for a benchmark or provide a damper model for some OEM, I need to open the damper, I will have to do studies on their flow characteristics. I need to understand the frictions and the oil characteristics. And so this gives us complexity. We have some lack of generality as well, asks for computer power, and most of the time, we are not able to run these on real time. So some points on these kind of simulations, they will ask for a very small step size that will kill all the power of the real-time simulations. So we, at Hitachi, we are working on a solution that will address these weaknesses of the lookup table. And we are offering a trained neural network model that is able to pick some trends of the damper that will bring together all the behavior on the damper caused by the fluid properties, the hysteresis, the friction, the gas forces, as well the thermal properties. So this subject is something that we brought on the last year on the zero prototype in North America. I was able to show the second generation of this neural network model, but we've been working on damper representativeness to enhance the immersion and the results for full vehicle simulations. For some years, I started with 1D models. Now we are on the third generation of these models that we put together a data processor that uses the data for the input as the lookup table, and we have the S function model that it's kind of predict the behavior of the damper based on some data sets that we provide them. So the way that we provide these data sets and the tests that we need to run to characterize these type of dampers, it's based on some know-how and based on the years that we've been working on these kind of models. So I will show some bench correlation tests. So what we do, we train these models with some proper data sets, and then we put these models to run on an unknown drive profile and other bench tests that we can check if they are behaving properly, that we can assemble on the full vehicle model. So over here, you guys can see all the black dots, they are measurement data. The yellow line, it's the damping force based on just on the lookup table, and the orange dots, they are the points from our damper models. On the histogram, we can see how is the error of the force from the measured data to the model. So the orange one, it's the neural network damper, and the gray one is the lookup damper. This, for example, is how is the passive model from a damper. We can see that we are losing some lag on the damper if we use just the lookup table as data. Over there, we can see on the blue lines that we can have a better adhesion to this model. Another application that we could find to apply this, it's very useful, are these, they are frequency dampers with frequency reactive devices that they add some lag, or they help the dampers to filter kind of some frequencies or react to some freaks on the vehicle. They are, like we can say, as passive plus dampers that they, if we are not going for a semi-active and you are trying to go for some ride improvement, you can use these dampers. For example, on these plots, over there we have one that's made by Hitachi, but this one, it's one that we use to as a benchmarking data, so we could train the model and get all these good results based on just on doing tests and not taking apart any part of the damper. This is another example how they behave, so we can capture most of the lag, we can consider that we have a good adhesion to these tests. Another application is for semi-active as well. Sometimes we go for runs, full vehicle simulations. We do some co-simulations with the logic together, but we mostly base our tables on 3 or 4 fixed currents. And sometimes we are not able to get the interpolation between them, or we need to do some calculations for that. So this is a good application for this kind of dampers as well, this kind of models. Now I'm going to show some full vehicle co-simulation comparison. So this is mostly running on a co-simulation based on the S function that we have from the dampers, and as well comparing with the lookup tables. So I ran the vehicles on some randomized surface or rough roads, did some steering events with very low steering inputs, and I used just a passive damper and a FRD damper as comparison. So we can see we can capture some hysteresis from the damper that's mostly presented on very low rod velocities that will have some influence on the whole behavior of the car. So that feeling that we will just sit on the car, that just small steering inputs, most of the time, if you don't have a good model, if you sit on a simulator, you are not going to feel nothing. Sometimes we just blame the tire models, but the dampers, they have some kind of participation on these as well. Here is another example that we can see some response on vertical acceleration, how the hysteresis is being captured for both front and rear dampers. And on the PSD, we can take a look how, so we use these FRD, that frequency reactive dampers, to try to low and improve how the abruptness and the jerkiness of the car is being on the overall of the car. On this case, using these kind of models, we can capture this difference. And if we are going to use these or send for the supplier to do the first take-aparts or the first prototype dampers, we are probably, if we are going to use the lookup table, we are probably going to miss some part of, we are going to ask for more damping or less damping that you are actually need to have on your vehicle. Another example is using the passive as well. We can see that we can capture a good amount of hysteresis. We can see response on vertical as well. So we just received at Hitachi some requirements for dampers for building take-aparts or first prototypes that we can see that they are just based on simulation. And after we provide them to the OEMs, we just hear that, oh, I overcooked the damper because I asked for too much force that I didn't need because I could see this on the simulation. So we understand this as a pain point that we can address with this kind of models. Over here, we can see as well some lateral body responses as well. So we can capture difference on both, most of those kind of metrics. Wrapping up, so our intention is to deliver the best performant damper models to be able to help the customer needs and be able to be side by side on this path for virtual. So these damper models, they have some capabilities for some tuning. They have they will enhance the subjective and objective evaluations during the driving loop session or just offline simulations. And as I mentioned, they can have some tunability because as we use the lookup table as base, but we need to do the training for the behavior of the damper, we can have some tunable range that we can achieve with this kind of dampers. And we can provide the dampers according with the OEM's needs. For example, we can run with higher speeds, dampers more focused on just ride evaluations, ride and steering, or if you need for durability, we can, now in our lab, we can have capability to run to up to 6 or almost 8 meters per second damper tests, so we can generate these kind of dampers. So, and as well, as we are delivering on an S function, we can do like DLLs, and as well, we can include on deliver as FMU to be ready to go on some Linux environments. Here is another example how we can enhance the damper representativeness on the model. So that's all that I can have to show. Thank you.